Good to see everybody. I'm going to share my screen and get started here because we have quite a bit to go through. And let's get into slideshow mode. And can somebody confirm they can see my screen?
Yep.
Great. Thanks, Ethan. Awesome. So welcome. Want to just introduce myself really quick, and then I'll spend a little time introducing others who are going to be definitely in the weeds doing some of the work on this project as we go. And of course, those of you who are familiar with CalTRACK and as it has existed in the past, there is going to be a lot of similarities here. So everybody who wants to can contribute ideas or even go deeper than that if they so choose. And so just for those of you who don't know me, I'm Adam Scheer. I am the Vice President of Applied Data Science here at Recurve. And we're really kind of here under the umbrella of the Linux Foundation today. And this working group is going to be under their charter. And I'll talk a little bit more about just kind of what that means later on, and others who are on the call who are familiar with that can chime in as well. We do have a somewhat large group, which is great to see, but I don't want people to feel like they can't speak or you know, have their voice heard during this meeting. So I think what I'd like to do is just, if folks want to chime in, ask a question, whatever it is, feel free to do so. Feel free to interrupt me, but I will keep the conversation going if I feel like we're getting too far behind. We do have quite a bit to cover, like I said. So thanks everybody for coming. And I just wanted to start off and provide like the agenda, because this isn't maybe exactly what you'd expect, but I want to make sure folks know what's coming here today. So we're going to start off with just like a brief history of CalTRACK and the OpenEEmeter. We'll then give a very quick methods review of the current methods, and I'm going to be very brief, so I will offend those of you who know the details here probably. Then I'm going to get into the meat of what we want to talk about today, which is CalTRACK 2.1 and beyond. What the anticipated areas of focus are on our end, and then hopefully hear some ideas from others. And then we're going to talk a bit about knowing some of the issues that we feel are important to tackle. What are the planned research that we have in front of us, and tools? And again, happy to get some feedback on that from folks and ideas. And then I'm going to just very briefly touch on where comparison groups fit in this whole conversation. And then we're going to hand the baton to Phil No, who is the Vice President of Engineering here at Recurve, and he's going to talk about GitHub and kind of some of the procedural elements of GitHub and where GitHub is today and how you can use it to be part of this project. And then I'm going to give like a brief people and process overview, introduce you to some of the technical steering committee and expected contributors, and then we're going to end on logistics. And if we have some time, which would be awesome, we'll have a little space for discussion at the end. I'm not sure if this meeting invite was an hour. I do plan on going a little longer than an hour, maybe even up to an hour and a half. So if folks need to leave, I apologize for that. And I do want to say just right out the gate that I think on the meeting invite and the information that was sent out, we had planned for weekly meetings. I think weekly meetings are a bit much, to be honest, and I think we're gonna try to space that out a little bit more, because this is very time consuming for a whole bunch of very busy people. So I want to make sure that everybody is able to kind of marinate on things a little longer than just like a weekly cadence. So we'll probably go like once every 2 weeks or once every 3 weeks, depending on what the needs are. Okay. So I'm going to dive in just right away with a brief history of CalTRACK and the OpenEEmeter. For those of you who aren't like intimately familiar with a lot of this, and I'll just say right off the bat, like I'm probably not the world's expert on all of this history. So if folks feel like I'm missing something critical here and you want to pitch in like that point, feel free to do so. This was kind of just out of my own recollection of a lot of these events and some of the written documentation that is available for everybody online. So really, the CalTRACK itself is a set of methods that allows us to calculate models for individual meters, energy consumption patterns, and then to project forward predictions of what the energy consumption patterns would have been for that meter in the absence of an intervention, oftentimes an energy efficiency program or other types of programs. We've even used CalTRACK to measure the impact of the COVID pandemic, for example, or other factors like time of use rates that impact everybody in the population. But that's sort of the fundamental, like, what is CalTRACK? It's a modeling framework in order to produce predictions of the energy consumption that would have happened in the absence of some kind of intervention that we want to study. Now, this got started all the way back in 2012, 2013. The CPUC issued a decision that directed some work be put into meter-based modeling in order to help calibrate building models that were being developed through various software tools. So these were like building simulation models that contractors could enter information about the home, the building, and then what interventions they were doing. Like, they were changing the insulation from a certain thickness to another thickness. They were putting in a new air conditioner with a Scheer rating of X, Y, and Z. They had blower door tests, things like this. You could enter all of that information into a software tool, and it would predict the savings that you would achieve in a given project. Now, the CPUC said, hey, this is all fine and well. And a lot of this was related to the Advanced Home Upgrade Program, which was a really key deep home retrofit initiative that the CPUC was driving at for a long time in California. And they said, we appreciate these models, but we really need to calibrate them. We don't necessarily trust the outputs of these models. So we need a way to verify what these models are producing. And we should do so based on metered methods. So CalTRACK got its like early start, or its roots are really at that time. Now, fast forward to 2015, and AB 802 passed in California, SB 350 passed. AB 802 established existing conditions baselines as the default in California. Now, before that, it was code baselines. And for those of you familiar with the energy efficiency world, when you have existing conditions baselines, the meter-based measurement or the meter-based change in consumption that you would measure is now directly applicable to the savings that you can claim for a program. And if you're using a code baseline, that is not the case, because the meter-based measurement takes you from existing conditions to the state of affairs after the program, whereas the code baseline is somewhere in between there usually. So it made meter-based measurements relevant and useful for actually claiming savings. After that, the CPUC kicked into gear and had some rulings, some decisions that established the first meter-based framework in California for energy efficiency programs. And PG&E then kind of hopped on and as well as a few other utilities, and launched meter-based programs. So around that time, leading into 2016, PG&E led the effort, and a number of contributors were part of that effort to establish the CalTRACK 1.0 methods. And these methods were focused on monthly and daily data. And along with those methods came the first version of the OpenEEmeter open source code base, which still exists today and is in use every day. Now, going one step further into 2017, the CalTRACK methods were in use in PG&E's P4P portfolio. They were in use in NYSERDA and other territories around the country. And the working group was back together and back at it, producing the CalTRACK 2.0 methods. And the 2.0 methods had improvements to the daily methods and established the hourly methods. So there are now CalTRACK monthly, daily, and hourly methods on the books. So when we get into 2019, OpenEEmeter itself was donated to the Linux Foundation as an open source project. And then 2020, we all remember 2020 very well, COVID hit, and all of a sudden we kind of had to figure out how we were going to measure the impact of programs when a global pandemic was having a massive impact on almost every customer's energy consumption. You know, when we did a lot of research at that time and found that in residential, COVID was having upwards of 10, 12, 15%, depending on kind of where you were and who you were, increase in an average customer's energy consumption. Similar story for the commercial sector, only a decrease in energy consumption. So we had to spend a good amount of time, like as an industry, figuring out how are we going to keep these meter-based programs going when we have this massive exogenous impact or external factor at play in the global pandemic. And then finally, just to round this out, CalTRACK has been also incorporated into the demand response methods that CAISO has available for settlement. And that is also a comparison group framework. And there's more information available at this link that I've posted here. So moving on here, like I said before, this was the work of many parties, many subject matter experts, regulators, utilities, a whole bunch of folks were at the table when these methods were being developed. So we're kind of standing on the shoulders of giants here. And I definitely, being at Recurve, we use these methods quite a bit. So it's good to see the folks back at the table today who were part of these initial processes even 5 years ago. Okay, so what's the purpose of CalTRACK fundamentally? What is the purpose of these open source methods? Well, we want to establish a standard weights and measures for demand side programs. I think we all realize that utilities for a long time have used supply side tools to solve most problems that impact the grid. And that's really not like the formula for the future anymore. We have climate change, we have grid resiliency, we have lots of renewables on the grid, higher saturations of solar power, more dynamic loads. And we really need the demand side of the equation to be an important part of the solution to all of those things. But it's hard to do that if the measurement itself is not fully transparent and standardized in a way that can be contracted and be a settlement mechanism. So we want to establish weights and measures for demand side programs. We want to enable our industry, the demand side industry generally, to compete at scale, including against supply side options. I think most people on this call are probably aware that energy efficiency is the #1 resource in the loading order in California. Yet it really doesn't behave that way. We don't treat it that way fundamentally. It's just kind of text in a law somewhere from the 70s. But we want to get it back to that point. We want to get efficiency, demand response, other demand side resources at the table as legitimate and scalable. And then finally, we want to remove barriers to measuring integrated interventions. I think the programs of the past are not going to look like the programs of the future are not going to look like the programs of the past. So why are we here now? Well, #1, existing methods can be improved. The existing CalTRACK methods are far from perfect. They've served us very well, but they're not perfect. And we have a lot of experience using them at this point. So we've learned a lot of where some of the weaknesses are and where the opportunities to improve the existing methods are. Secondly, we have the opportunity where methods, advancements, and specifications can open up a new batch of use cases. Things like integrated efficiency and demand response, solar and storage. Like I said, and I think we all understand this just kind of inherently, the programs of tomorrow are not going to look like the programs of yesterday. And so, yeah, times they are changing, right? So just fill in the blank here. The industry is changing fast. The energy industry is changing fast. The utility industry is changing fast. Our industry is changing fast. And why is it changing fast? Well, the electric grid itself is becoming the hub for broader decarbonization. It's not just decarbonizing power plants. That's not the game anymore. It's decarbonizing transportation. It's decarbonizing buildings. It's decarbonizing through the use of solar plus storage and giving the grid that much needed resilience when we have a high penetration of renewables. So distributed energy resources in general are being utilized and integrated into the electric grid system in a way that they never were before. This obviously is creating a huge stress on the grid, and it gets back to some of my earlier statements about the need for demand side resources. So we need measurement capabilities that will enable, not inhibit, these types of modern programs and the aggregators who can bring them to bear. Okay, let me stop there just really quick, see if anybody has any comments, questions, thoughts on what I've covered, and then I'm going to get into a quick methods review and then where we want to go at this point with some of the existing methods. I see James. Yeah.
Hi there. Yeah, so one question, I suppose, is on whether CalTRACK is meant to calculate site level savings or portfolio level savings.
It's a really good question. CalTRACK fundamentally is an individual meter model. However, it's really not designed to be that highly sophisticated, specific model for every single building out there, especially on like large commercial. So there is a lot of statistical variability in energy consumption year over year for most customers. If you look at the residential sector as an example, the standard deviation in the difference of year over year energy consumption is almost a megawatt hour. That's like 8–10% of a typical customer's usage, even more in California. And when you look at that, and that's just year over year energy consumption, and you can even weather normalize that, the value is about the same. We know that we have a lot of just change that's happening in a typical customer's circumstances. So given that, if you want to use CalTRACK, or if you want to use any model to really get into like what was the individual project savings, you need to account for a lot of those factors. You know, the typical things like the cliche things like somebody had a baby, somebody's kid went off to college. Those things are very real. And they have significant impacts on energy consumption. And we're probably not going to be putting a kid went off to college variable in CalTRACK.
That's great.
Yeah.
Thanks.
Other questions, other thoughts? Okay, I'm gonna keep moving and we'll have plenty of time for discussion, I think. So I want to start with the CalTRACK daily. So the way CalTRACK daily currently works, this is just a graph that shows you like how a model is overlaid on meter data. This is a good example to think about with respect to like gas consumption. Now we have the average temperature, average daily temperature on the x-axis, and on the y-axis we have the total therms consumption for any given day. And this is just, think of this as a meter. This is a meter. And so the model that is generated to fit this data has a few components, and the model is shown in the red line. So first is a balance point temperature. So the balance point temperature basically says where in this meter's usage do I start to see increased consumption as a function of temperature. And outside of that region is a temperature independent region. And then to the left of the balance point temperature here, or at colder temperatures, I have a linear model that we fit. So it's basically a piecewise model where we have a temperature independent region, balance point temperature that is identified in the optimization process of the model, and then a linear region, and this HDD is a heating degree day. And I'll talk a little bit more about what exactly that is. So these are the components of the CalTRACK daily model. Now, what I showed you was an example for gas. In reality, there are 4 distinct CalTRACK models that can be fit to data, and we will fit each one and choose the best one for the particular circumstance on a model by model basis, or on a meter by meter basis, I should say. And these range anywhere from a completely temperature independent model all the way through to a model that has a heating balance point temperature, a cooling balance point temperature, and associated slopes. And a model like that, you might expect for a customer that, for example, has electric heating and has electric cooling, or has a reason that their energy consumption increases in the wintertime as well as in the summertime when the temperature gets cold and when the temperature gets hot. So this is fundamentally the way that the CalTRACK daily model is formulated. It's not insanely complicated, but it's not super simple either. These balance point temperatures are variable, and they're determined via an exhaustive grid search. So every single degree is tested to find out if that degree, putting the balance point temperature there in the linear regression that follows, if that particular point is the best possible point to fit the data on hand. And we'll talk a little bit more about opportunities to simplify some of the grid search functionality, which is computationally very expensive. Okay, now the hourly model. I'm not going to dive super deep on the hourly model. There's much more that goes on in the hourly model. For those of you who are familiar with the terminology, it's a time of week and temperature model, meaning that the model parameters or the variables are the hour of week and the outdoor temperature. It's a piecewise linear model, so there are a number of temperature bins for which data are fit independently. And so in addition to those aspects of the model, there's also an occupancy parameter, and there's this building state. So seasonality in the CalTRACK hourly model is captured. It's not really captured in the daily model. I'm going to talk a lot more about that. But seasonality is captured by producing independent models for each month. So every single month gets an independent CalTRACK hourly model. So the time of week aspect of the model is for specific timeframes that each month is utilizing to develop a distinct model. And then all of those models are basically sutured together for the annual CalTRACK hourly model. So there's a lot of details that go into this. And in particular with the occupancy detection or like the building state, there's like an initial regression that's done. There's a lot of details around how the temperature bins are determined and what data sufficiency needs are for each of those temperature bins to avoid poorly fit models or overfit models. So there's quite a bit, and there's a lot of documentation. We have a lot of links in this deck that will point people to like deep dives on any of these things if you want to look that far. So once you have a baseline model, and that baseline model is developed on a 365-day pre-program period or pre-intervention period, then you can produce a counterfactual. And that counterfactual uses the model parameters that were optimized during the baseline period in order to predict the energy consumption in the reporting period or in the post-program intervention timeframe. And the way this is done, if you think about the daily model, the temperature is the variable in the daily model. So you take the temperature data of the reporting period and you plug it into the baseline model parameters, and that gives you a prediction of what energy would have been consumed in the absence of the program. And that is called the counterfactual. So the difference between the actual observed consumption and the counterfactual is the savings. That's the savings in the CalTRACK model. It's not crazy complicated, really, but it's good to go over this because that counterfactual is everything. You know, the counterfactual is having reasonable counterfactuals is really what makes a model a good model or a poor model. Okay, so I think I'm going to go through this section, then I'll stop for questions. And then Travis Sykes, who is a lead data scientist at Recurve, is going to take the baton and talk a little bit about addressing some of the issues that we would like to bring to the forefront here today. So CalTRACK Daily, let's start with CalTRACK Daily. We know that there are specific areas of model bias. And the question we have is, can we improve the known biases in the CalTRACK Daily model? And I'll talk more about where we know these biases are. So secondly, are computational and efficiency gains achievable? You know, I think it goes without saying that in large portfolios, we need to have a model that can scale. We need a model that doesn't take 20 minutes to formulate and run. We need parallelization. We need, you know, these models to be able to operate on portfolios of millions of meters potentially. So computational efficiency gains would be a very welcome thing. And, you know, potentially improve modeling for solar PV customers. This is an aspect that we're all grappling with now. You know, more customers have solar, and we'd like to be able to include them in programs. In fact, they would be very worthy of prioritizing in our programs. They have solar. They're likely to be customers that have something to offer. The grid, CalTRACK hourly. So there are a number of known, like very small bugs, and it would be good to just fix those, to knock those out. We'd also like to specify demand response baselines and appropriate model modifications. This whole annual CalTRACK model that I talked about earlier, suturing together a lot of monthly models, that doesn't necessarily lend itself immediately to the demand response use case. So we've made some progress on this already, working with the California Independent System Operator. And we'd like to bring some of that information, those findings, to this group and talk about how DR baselines can be established within the CalTRACK framework. Solar PV modeling, this is a big one. It's like I said earlier, in particular with the hourly model, where when we have AMI data available, we'd really like to be able to understand the usage patterns better of solar PV customers, and to be able to model those usage patterns more reliably and produce, again, counterfactuals that are responsive to the types of weather patterns that impact solar customers that do not impact non-solar customers nearly as much. If it's the sun is shining or if it's a cloudy day, that has a big impact on solar customer energy consumption. So we have some ideas here, but this is a big one. Improving the functional form of the CalTRACK hourly model. I think we'd like to dive back in and understand things like overfitting. We'd like to understand things like the linear nature of the temperature bins. What can or should we do with respect to functional form of the model? And then developing specifications for additional use cases. So, and then finally, there's EE weather. I haven't talked a lot about EE weather, but EE weather is a huge part of this because all of these calculations rely on having temperature data, at the very least temperature data. And we'd like to expand some of what EE weather is doing in order to bring in like solar data, for example, solar irradiance data or cloud cover data. And in talking with some folks just leading up to this meeting, several people mentioned to me that having a little bit more functionality and a little bit more ease of use with EE weather would be a very good thing. So now, having said all of that, Recurve is willing to devote resources to many of these problems, but we can't solve everything at once. So what is it that we kind of want to carve off for the next few months and like some intensive R&D efforts in the next few months? So I just want to highlight these things because these are the things that I think, given the resources that we have available, which obviously are not infinite, we would like to tackle these things right now, but we would like to move on to these other things very shortly after. So I don't want to just say, hey, these are the things we're going to tackle now, and then we're going to close the book on this for another 5 years. I don't think that's anybody's intention. What I would like to do is focus on these things because these are really important aspects of modeling building energy consumption and the portfolios that are already in existence today. In particular, the CalTRACK daily model is very important for gas. Most utilities do not have hourly gas data. So the daily model will continue to be a very important aspect of measuring entire portfolio performance. Okay, let me stop here and just see if folks have any questions or concerns, any other big things you think we're missing right off the bat. Yeah, James, go right ahead.
Thanks, Adam. Yeah, James from Carbon Co-op again. So yeah, we're doing a project to look at kind of how we can adapt CalTRACK to the UK and kind of try and start to roll this out in the UK. Mm-hmm. So, I mean, it's not been highlighted in your as a priority here, but we have effectively replicated EE weather. So, I mean, that's essentially using, I don't know if you know about the Copernicus temperature data. This is sort of available from the European Space Agency's website. Mm-hmm. And essentially they've just got an API that anybody can use. And you can link that up to your like postcode or zip code, and then that's quite an efficient way of well, it's an easy way of getting it. It's not that efficient because it's quite computationally intensive once you've got these are quite big files you're dealing with. But yeah, I'd be happy to kind of talk you through that.
Well, this is great. This is one of the things I kind of wanted to understand from today's meeting, if at all possible, is who may be able to help in EE weather. I think there are a number of users of EE weather, and actually EE weather gets utilized even outside of the OpenEEmeter context. So I think a number of folks have some potential contributions that we would love to have your contributions here. And I see Ethan has his hands up as well. Ethan, yeah, what are your thoughts here?
Sure, and happy to help out with EE weather stuff. So a couple things. One, just staying on EE weather, the TMY3 data is not so typical anymore since the temperatures are going up. So it's a challenging problem of like if you're doing a 30-year forecast or even a 10-year forecast, and now we're using this like 10 to 40-year-old data. And so I'm hearing from a lot of clients who are not really feeling confident about the forecasts that we're getting with TMY3, but it's a non-trivial thing to come up with new hourly data. There's some, long-term forecasts for lower granularity weather, but anyway, so that's one area. And then the other is that as we're seeing more heat pumps and more hybrid systems, the number of parameters that we have in the CalTRACK model, just talking daily now, isn't really cutting it, right? So you've either got a hybrid system where the electric load is increasing with colder and then temperatures, and then it cuts out, at 30, 20, whatever it's configured to. And so that data is modeled really poorly by CalTRACK currently, or conversely, then you have the gas system, which might be picking up at 20, but it's not picking up from 0 because the base load isn't, that's not really how it intercepts. So maybe the gas one is not as big a problem. I haven't looked as closely at those because frankly, it's monthly data. And so it's a little harder to figure out what actually should be going on. But definitely the electric side is a bit of a mess with heat pumps, not even getting into like second order effects of the variable COP, just dealing with that low temperature cutoff.
Sure. I'm glad you brought up TMY3, especially because it's the thing I forgot to include here. I remember talking with you about that previously, and I was like, I know I'm forgetting something on EE weather, and it was the TMY3 thing. Yeah, couldn't agree more. Using weather from like the 80s or whatever isn't exactly representative of our climate change reality today. Thanks for that, Ethan. Let's follow up on some of those points.
Sure.
Steve, I see your hand is up.
Yeah, I think Greg was first.
Oh, okay, Greg. I can't see everybody with raised hands, so help me out here.
Okay, maybe not.
Yeah,
yeah,
go right ahead.
I'm thrilled with the focus on reducing bias or improving the accuracy of CalTRACK. One thing you didn't include is maybe the development of some type of test suite or some way to track progress going forward against some type of ground truth or some at least test suite of buildings, so that we know with each change to CalTRACK we're improving things, not making some buildings worse.
Yeah, good point. So number one, regarding like a test suite, Travis is going to talk quite a bit about how like the elements that we anticipate putting in place for some of the rigorous testing that we know needs to be done here, because obviously we don't want to just be kind of winging it. Looks like it's good over here in these 5 buildings. We need to be testing large portfolios and understanding where things are improving and what the pitfalls are. And then regarding your point about like, yeah, so on the data front, I think we are close to some agreements with a few utility partners to at least enable us to have access to data and use it for this working group. I wish I could provide data to everybody just like, here's a massive data set of, 100,000 customers or whatever it is. We're really not in the position to provide that data just contractually with, what we have on hand. But what I can guarantee everybody is that we definitely will be showing results on like large portfolios and digging in and getting input from everybody on how to slice and dice everything if you want to look at specific cuts or whatever it might be.
Yeah, and I hope you'll also consider using artificial data sets, either from energy building modeling tools like CPUC Res, or made up data sets. I
think we're willing to do that, Steve. I think the issue I've seen, and I think actually I'd like to go into this next section, like having that in mind, is real world consumption data is very nuanced. And I have yet to see like a synthetic data set that really can reproduce some of those nuances. Having said that, I'm willing to, we're willing to put some of those things to use if we collectively feel like it's it meets the mark. Ethan, did you have another comment?
No, I was just going to offer we have some synthetic data, but you're spot on. That it's questionable whether it actually does the job. So frankly, we'd probably have to like test the synthetic data against some real data and see whether it exhibits, similar dynamics. And so it's a bit of a challenge.
Yeah, it's a good point. Okay, thanks for all of that. Let's come back to this discussion pending having some time for it. I'm going to keep us moving here. And I kind of want to get into like the actual areas of bias in the CalTRACK daily model. So, know thy enemy. What are the sources of bias currently that we're aware of that are substantial in the CalTRACK daily model? So there's 3 of them, and there may be more, but these are the 3 that we kind of know and understand and have tested. So there is weekday weekend bias. There is no flag in the current CalTRACK daily model for specifying whether a day is a weekend day or a weekday day. And obviously buildings have different energy consumption patterns oftentimes during the weekends versus the weekdays. And I'll show an example of that in a moment. We also have seasonal bias that we know exists. So the winter, for example, tends to push savings high or low, and the summer tends to push savings high or low. I forget which is which right off the top of my head, but I'm going to get into that as well. And then we have like thermal lag and behavior. So if it's cold, like 3 days in a row, then people tend to need to heat more. If it's hot 3 days in a row, then people tend to cool more, those kinds of things. And we've done some testing on this front as well. So I want to get in right now to a bit of what we've found actually looking at weekend weekday bias. Well, really, I'm going to focus mostly on seasonal bias and thermal lag, because the weekend weekday is just kind of like commonsensical, right? And so looking just right at the gate, like this is a CalTRACK daily model shown in orange. And this is a building that clearly has a very distinct usage pattern during the weekend compared to the weekdays. Weekdays are shown in blue, weekends are shown in the green diamonds. And the CalTRACK model itself is just trying to split the difference. So it's never really modeling anything particularly well. It's just splitting the difference between the weekends and the weekdays. Now, this is not as severe as might meet the eye, because almost all of the time that we're the use cases that we have encountered, at the very least, I don't want to speak for everybody, but at least that we have encountered, you're typically using CalTRACK daily results aggregated over the course of at least a month. Now, that doesn't mean that you're not introducing at least some bias in those aggregated monthly numbers, because some months have a different number of weekend days versus weekdays, and that can change over, as the calendar changes. So this is an issue we would like to address and that we're well aware of. Okay, seasonal bias. I'm going to spend a little time talking about seasonal bias because I think it is quite important, and I think that it's something that you could ask yourself, why is there seasonal bias? It's one thing to know that there is seasonal bias. It's another thing to kind of like really figure out why it is there. And I'm going to try to explain why seasonal bias exists in the CalTRACK daily model. So feel free to ask questions if I'm losing folks, but I'm going to do my best to explain this as clearly as I can. So first and foremost, I just want to explain this graph. The x-axis is the average temperature, the average daily temperature minus the heating balance point, and we're looking at aggregated data. So the reason we're using this metric on the x-axis of average temperature minus heating balance point is it allows us to put everybody on the same apples to apples basis. If I were just using temperature on the x-axis, well, some people have a heating balance point of 40. Some people have a heating balance point of 55. Some people have a heating balance point of 75. Changes for everybody. So if I'm looking just at temperature and I'm looking at bias as a function of temperature, then I'm kind of mixing all of these different customers together in a way that doesn't actually highlight the problem. So I'm looking at the average temperature minus the heating balance point, that delta. So anything below 0, you are in that linearly increasing region. And these are gas meters we're looking at now, and these are like a large aggregation of meters. And then anything to the right of 0, and you are in that temperature independent region of the model. So one thing I want to point out right away is, so the left-hand graph, the green curves are shoulder period. The middle curves are summer in red, and the right-hand plots are winter in blue. The bottom graphs are showing the observed, the aggregated observed consumption. Those are the open data points. And then the model, the aggregated CalTRACK model is shown in the solid line. So if I look, for example, at the bottom left-hand graph, this is the shoulder period. And by shoulder, I mean May, April, or it's like March, April, May, and October, those kind of like mild spring and fall months. If I'm looking at the shoulder season, I can see a few things. Number one, the model is under predicting consumption right around the balance point temperature. And as I continue into the heating region, further left in the graph, then I see that the model switches and starts to overpredict. And the upper left-hand graph is showing the actual error profile. So it's showing the difference between the observed and the model, and it is just expanding that across the y-axis so you can see it more readily. Now, the summer has its own distinct error pattern that emerges. And what we see in the summertime, looking at that bottom middle graph, is number one, the model it tends to overpredict at high temperatures. And then as we get closer and closer to the balance point temperature, we see once we cross that threshold of the balance point temperature, the model substantially overpredicts consumption. And that leads to the error profile that is shown in that upper middle graph. Okay, moving finally onto winter, I can see there is a pretty substantial under prediction of energy consumption as I am around the balance point temperature. In particular, like when I'm right on the balance point temperature, I have a pretty substantial under prediction. And so in each one of these cases, the error profile is distinct. It's different in each season. So that's one sort of key takeaway. And if I'm looking at the winter, then I see that customers are, generally speaking, starting to heat their homes at a higher temperature than the annual CalTRACK model would predict. And as a result of that, the summer and shoulder periods effectively have to make up for that. Remember, this is an annual model. Bias over the course of the entire year is going to come out around 0, or it should come out around 0. So if you have significant issue in one season, then that is going to almost by definition manifest itself as opposite issues in other seasons. And that is exactly what we're seeing here. So what are we trying to do here? We're trying to understand why is there bias why is there seasonal bias in the CalTRACK daily model? And the answer is basically that customers don't have the same heating pattern in the winter as they do in milder shoulder months or in the summer months. So that fundamentally is kind of the answer. And then everything that stems from there is the model trying to balance that effect in other seasons, trying to make up for it so that the annual bias is near zero. Okay, that's a mouthful. I'm going to just get through the seasonal bias discussion, and then I'll stop and see if there are any immediate questions. So I've kind of explained this. I probably should have used the animations that I generated. Let's look at an example. So this is that very same model that I was showing earlier. And these are 365 data points plotted along with the model that's generated in the baseline period. Now, we see that the heating balance point temperature is about 63 degrees. And everything kind of looks reasonable, right? It sort of looks okay. But let's dig a little deeper. So, and then just to orient you toward this graph and kind of what I'm going to be sharing, this top graph is taking every one of the data points on the bottom graph, and it's looking at the residual. So it's looking at the distance between the model and the actual observed data. And then on that right-hand axis of the upper graph, the black line is the cumulative error that I've calculated starting with the lowest temperature and ending at the highest temperature. So this pattern, you can see it kind of flips sign around the balance point temperature, which is pretty consistent with what I was showing here. But it winds up coming back about to zero, which, like I keep saying, you have an annual model, your bias for around the year is going to end up around zero. All right, so now what happens in the winter? Here, I'm just isolating the winter. So I'm showing the CalTRACK daily model exactly as it was on the previous graph on the bottom. And I'm showing the winter data points. And on the top, same kind of thing. I'm just showing the error that exists for each one of these data points relative to the model. And the dark blue line is the cumulative error that I'm summing up for every single data point as we go from the lowest temperatures to the highest temperatures in the winter. And we see that in the winter, we wind up with a whole bunch of data points that are too high around the balance point temperature. And then even as we go into the very lowest temperatures, the model tends to be a little low. So we're under predicting consumption in the winter, and we wind up with negative bias in the winter. We look at the shoulder, it's very different. And this is the model's attempt to swing things back toward zero bias. And what we see in the lower plot is clearly we have a cluster of data points there around like 60 degrees, just sort of below the balance point temperature. And that cluster of data points is by and large, far too low. And that's yielding a model over prediction. And so the savings measurement is biased high in the shoulder period. And then when we look in the summer, we see kind of this effect that, as we get further out and further out toward hotter and hotter temperatures, we see somewhat increasing model bias. And that's really because it's trying to balance some of the squirrely predictions around the balance point temperature with this temperature independent region, which just has to be a total flat line leading out to the hottest data points. All right, so fundamentally, you might ask, is this just something that exists with a handful of meters and all the other meters are just fine? Or is this something that is more systematic? Does this occur with most meters? And so we've looked not only at like the aggregated results that I've shown here, and an example, one specific example shown here, but we've also looked at distribution of many thousands of customers. And what I'm showing is the distribution of wintertime bias in the CalTRACK daily model for gas. It's pretty obvious. I don't need to explain this a lot. It's pretty clear that this is a pretty systematic effect. It is there for most customers. When I look at the summer, it's very different, but it is also there for most customers. And I can show the shoulder. The shoulder looks a lot like this too. So this is why there is seasonal bias in the CalTRACK daily model. Let me stop there and just see for a couple minutes, and then I want to move us on if there are any thoughts about this.
Yeah, this is Steve again. I think we've seen this for all the homes we've analyzed, and we see that getting the balance point temperature correct is very, very difficult for many, many homes, and it changes throughout the year.
Yeah.
So those two things are critical. So I would say that improving the method used to select the balance point temperature in CalTRACK is a key goal.
Thanks, Steve. Totally agree. All right, I'm going to move us on. This is just kind of an interesting side note, which is we've also done this analysis for the CalTRACK hourly model, and the bias pattern exists. There is a bias pattern, but seasonal bias itself tends to not exist. So if I'm looking at these numbers in the lower left-hand corner of these plots, I see that the average customer, the average daily error is about 0.14 therms negative in the winter, and then 0.7 therms positive in both the summer and in the shoulder period. But in the hourly model, like that bias doesn't really exist across the season. But there is a pattern that, interestingly enough, because the hourly model doesn't really have a balance point temperature, but I'm still plotting it, against these balance point temperatures that were determined in the daily model. So there is a pattern here, which is very intriguing and something that we anticipate coming back to when we're focused on the hourly model. Okay, finally, I'm gonna move us on here because we still have a bit to cover. Thermal lag error. So now on the x-axis, I am looking at the previous day's average temperature minus the modeled day's temperature. So anything to the left of 0, the previous day was significantly colder than the day in question, and anything to the right, the day was hotter. And as you get further and further away from 0, that that temperature difference grows and grows. So again, shoulder, summer, and winter as we go from left to right. And you can clearly see that, there is a real impact that previous day's temperature has on current day consumption. And I went the wrong way there. This is just, again, blowing up that error profile itself. And you can really see, this is a real thing. So, I don't think any of us doubt that this is a real thing, but it's nice to have a measurement of it. And so this is another issue, getting back to those 3 areas of bias in the daily model: weekend, weekday, seasonal, and thermal lag / behavioral. These are things that we are well aware of. Okay, so I'm going to talk about or I'm going to hand the baton to Travis. But before I do, yeah, Ethan, go right ahead.
Well, sorry, I just, on that last slide, just wanted to double check and make sure that I heard you correctly on the sign, right? Because if we look at that far right-hand graph is the winter data, right? That's the most.
Oh, yeah. Thank you, Ethan.
That's the strongest one. So now, so just my question on that is, I thought I heard you say that to the left of 0 are where the previous days are colder than this day, but it looks like it's showing that the model is under predicting. And I would have thought that the thermal lag would mean that if the previous days were colder, that the actuals would be less than the model, right? That there would be effects from the cold days dragging down the
keep in mind that we're in the heating region here.
Oh, right. Sorry. It's energy use. The model's under predicting, and okay. Sorry.
All good. It was a test. I wanted to see if anybody was following. Yeah. Thank you for that. Yeah, Greg, go right ahead.
Yeah, sorry. Hopefully you can hear me. So I think there's a lot of things to consider here, and I'm glad we're talking about this. Some of this is the second day of heating or cooling. The building shell maybe hasn't cooled down or heated up. But I'm also wondering, in terms of like long-term seasonal changes, there's things I'm wondering that could be incorporated in the model. that could help account for some of this bias. So, you know, in the spring, ground temperatures are still cool compared to the fall where they're warmer.
Yeah.
Humidity, you know, depending on your climate, that's an impact. Insolation. I'm wondering, you know, like how you plan to sort of account for this bias, and if any of this could be sort of included in the weather, you know, to help sort of smooth out some of those types of non-air temperature related sources of, you know,
yeah, good question. So I promise that Greg is not a plant, but Greg, that is exactly what I want to hand the baton to Travis to discuss, actually. So just by way of introduction, Travis has been at Recurve about a year now, and he is a senior data scientist here. He comes to us from the world of chemical kinetics, which actually is the world that I came from before I was in the energy industry. He specializes in numerical methods, model development, statistics, and has done some really good work here on comparison groups, and is now diving into a framework for how we might get at some of these issues. So Travis, I will go ahead and move through the slides if that's okay, unless you really want to grab the screen. But just let me know. Oh, before I do that, I have one last slide, and it is just to say, you know, that all of these things are testable, and I think we're already showing that, like, we can identify bias, we can wrap our heads around these things, we can quantify these things. What ultimately should guide our thinking and our decision making? And there are a number of things that I've put here, but these are kind of like in our thinking through what is an ideal case. An ideal case is a model that doesn't have significant sources of bias, a model that produces low uncertainty, a model that is predictive, a model that is not prone to large degrees of overfitting, a model that is simple instead of a model that is complex, a model that is interpretable, and a model, finally, that can be run with low computational expense. I think, obviously, some of these things are in some conflict with each other. So we're going to have to make some decisions about whether, for instance, some degree of increased complexity is something that we want to take on at the expense of greater computational expense and potentially a higher degree of overfitting. And maybe a little less interpretability. So these are, I think, fairly obvious things, but it's just to say that I want, and I will commit to this group, that we are going to be presenting metrics. And those metrics that result from research and development efforts are going to be guiding how we want to think about these things, and should be giving us a clear picture of whether something is an improvement or not. So let me hand the baton to Travis, and Travis, take it away. Let's address Greg's question and some of what we've been thinking about here.
All right, so this is a characterization of what you can kind of expect, and this might seem extreme, but we actually see real world meters that look not unlike this in some cases. So here, what I show is energy usage on the y-axis and temperature on the x-axis, where temperature is increasing to the right. So on the left side in purple is winter. The shoulder months, spring and fall combined together, are the green, and then summer are in blue. And what we would currently get if we ran CalTRACK 2.0 would be a model that tries to go through and slice through the middle of all of that. So you end up under-predicting winter, over-predicting shoulder, and yet again under-predicting summer. All in all, if you run this for the entire year, you're going to, and you aggregate all of that together, you're going to see the exact same effects that you would expect as what Adam just showed. So what we are considering doing instead, if you can move to the next slide, is to instead keep the same models, but split by seasons, and then fit the models based upon those splits. For example, the better choice here would be to split winter up to its own model, which would then, in the next year, anything that is designated as winter would follow this model. Anything in the shoulder would follow this, this nearly temperature independent model, and the same for summer. The complication here is really one of not wanting to make things more complex than they need to be, but I'll get to that in a little bit. So let's just go ahead and jump to the next one. Or actually, better yet, are there any questions over the proposed solution for seasonal bias? All right, I'll move on. Now, weekday weekend is basically exactly the same. The problem that we're seeing here is one of the temporal domain being pushed onto this temperature and energy usage plot. And so the easy way around this is to do the same solution, where instead of on this, the diamonds at the bottom would be the weekend, the weekdays are up above. And the model here is trying to split in the middle. So you end up over predicting and under predicting, just as you would expect. Now, if we use the same solution as we did with the seasons, next slide, then you can basically say, okay, we're going to keep all of the seasons together, except we're going to break apart the days based upon weekday and weekend. And if we do that, you end up with your characteristic heating degree day, temperature independent region, and cooling degree day on the upper plot, which represents all of the weekdays. And then on the bottom plot, where this business or house or something, they basically just shut down during the weekend. So their energy usage drops to practically nothing. And it doesn't really have much of a connection with the temperature at all. So it's temperature independent as well. But it could have its own unique model as well if it has any sort of temperature dependency. So I mentioned overfitting, and this becomes a serious problem at this point, because you have to actually think it's not just about combining these things together, because we as people, we're very good at picking out patterns. It's hard to teach the computer to do the same thing in an intelligent way. So for us, when we look at this left plot, we would say, yeah, that fits great with one single model where it has a cooling degree day and a heating degree day. But how do we tell the computer that we don't actually want it to split up the weekend and the weekdays, which are all mixed together, because this building doesn't have much of a difference? How do we tell it that it should actually connect winter and shoulder as well as shoulder and summer? We could fit an individual model for all of these separate splits, but that would definitely go more on the range of we're beginning to overfit. Now on this right plot, it's an example of the combination of the two plots that I just showed, where this is showing some sort of seasonal change in behavior as well as a weekday weekend change in behavior. And the thing is, we have to make a model that can basically do the left-hand side and the right-hand side at the same time. Next slide. So one way that we can approach this is to basically isolate the correct complexity through a model selection criteria. This is something that's already done if you think about the different kinds of models that Adam was showing at the start, where you can eliminate cooling degree day from some models, you can eliminate the heating degree day from some models. And the way that we choose this is by penalizing our residuals based upon the number of coefficients with the degrees of freedom. So what we want to avoid is the maximum number of splits every single time, because then if you look at these kind of characterizations on the right, you would hit that far right plot where you are overfitting your data, and it's going to fit very well during the baseline, but then it's not going to be very predictive in the future, which is the entire point of these models. Now, on the other side of things, we have kind of where we sit at today, which is where we are basically underfitting these models. And so then you end up on the far left where you have a line, it's an ordinary least squares regression, so it fits reasonably well in the baseline period, but then you go into the reporting period and you end up having these seasonal biases, as well as this additional error created from having the weekday weekend biases. So where we want to end up is really in this middle plot, where we fit the general behavior, but we don't start drawing a little scribble line through all of the data points. Now, one way to, the actual ways to go about dealing with this would be like an adjusted RMSE, where for the root mean squared errors of the residuals. You can then penalize those based upon the number of coefficients that are going into your model. And we can basically just say, okay, well, each split is going to represent X number of degrees of freedom. And then we just add those degrees of freedom to the number of coefficients, and the model is penalized. We could also do this with the AIC, which is a Kaiki information criteria. I would personally go more of the route of the corrected version, which works for smaller sample sizes. As we would see, when I say small, these are made to work with like less than 1,000. We don't have years with more than 1,000 days. Same kind of thing for the Bayesian information criterion, which would be the next one, and then the next level beyond that would be like deviance information criterion, the widely acceptable information criterion, and the Wakabi Bayesian information criterion. Now, as I in general here, as I am listing these downwards, these are getting a little more complicated. They're requiring a bit more computational cost, particularly the jump from BIC to that next line. So the hope, basically what we can do is we add all of these penalties in, and then whenever the fit to the model is not justified based upon the penalties that we are imposing, it says, well, you don't use that, even though it might have lower error. It's not justified by the penalties. And so that's how we can kind of orient ourselves so that we pick the best model. Next. Now, I don't remember who it was, but they mentioned thermal lag. And basically what I'm showing here is now this plot's a little different from everything that I've shown you, and the same techniques that would work for the prior ideas will not work here. Because if you look, on the y-axis, I now have temperature, and on the x-axis, I have time. So now we actually care about that temporal component. So if this is just a characterization, but the orange plot here shows the outdoor temperature. And the blue curve here shows what a building's indoor temperature might be. Well, it's not going to correspond one-to-one because it's going to take some time for that energy to penetrate through the insulation, for the radiation to get through your windows, and for that to start to heat up your house. So it's going to take some time before that happens. And then why that matters is because that is also going to correspond to like the AC needing to turn up in order to shed some of that heat. So there's this lag time between the outdoor temperature and the indoor temperature. And if you can go to the next slide. Now, what we could do is that we could lag the day's temperature by some amount, because a building is pretty much, unless it has some sort of an intervention, it's going to have the same amount of insulation. It's going to be largely behave the same way throughout the year. I'm kind of neglecting the behavior component here. It is important. We're just kind of crossing our fingers and hoping that it fits in with this. So what we could do is, like right now, when we are running this model, we are saying that the temperature is the average temperature of that day. So here on this plot, it would be from like -24 to 0, where the time here is in hours. And that would just be how we then, all of the accumulated energy usage during that time period is assigned to that temperature. What we could do instead is we could lag that, where I show the dashed lines here. This is about a 36-hour lag. So maybe the house is it corresponds better to a 36-hour delay than it does a 0-hour delay. We could also get fancier with this, and maybe we don't just do a simple average. Maybe we do something, some sort of a weighted average like this Gaussian that I'm showing here. All of these are kind of options that we're thinking about exploring. Are there any questions about thermal lag or ideas that we might incorporate?
Yeah, James, go right ahead.
Yeah, just an open-ended one really on, I suppose, how would you evaluate the kind of correct lag time for each model?
So the way that I'm thinking about it right now is to basically have like a preliminary evaluation model where we fit everything to a given time period, like 0 hour lag. And then once we have those coefficients set, we can then go in and we can change the lag component, which will just change the temperature bins. And so whenever those what I'm imagining at least, is that if the lag corresponds correctly, then basically the error should decrease, and you might even be able to see that on a plot where if these things correspond well, the variation within the data, it should actually shrink.
And then you might have to do kind of devise a process that you could then repeat after an energy conservation measure has been put in place, because the lag is likely to change after that point.
It is likely to change. However, the entire point of what we're doing is not to anticipate a change. It is to be able to properly predict the baseline into the future. So we don't actually want to change the building's lag, because we want to see how the building changes whenever you increase the amount of insulation, for example.
Okay, cool. Thanks, Travis.
All right, we can move on. Oh, Steve?
Yeah, I've written about this in CalTRACK before, but what we found was, at least for homes, was using a rolling average worked great. So more and more buildings are doing pre-cooling and preheating, so it's not just a thermal lag. There's also the opposite, where the energy use precedes the temperature change. Just using we decided on a 5-day rolling average for both the HDDs and the energy use, and that seems to work really well.
All right, I think that's a pretty good idea, and add that to the list.
Thanks, Steve. Travis, do you mind if I keep us moving here, only because we are 13 minutes from the end?
Yep. Go ahead and jump past the ordinarily squares.
Let's jump into the cross-validation quickly, and then I want to make sure Phil has a little time for the GitHub discussion.
Yep. All right. So I'm going to go real fast. Cross-validation. Imagine you have the full set of data here on the left with the gray bar, and you want to split that into a test and a train set. The train set, we'll say, is 70% of the data. The other 30% is the data that's being held aside, is not used at all until the final test validation to basically see what kind of errors you're looking at. So then we go into doing the k-folds, which is the cross-validation process. Now, what I'm showing here, the 10% of the data and the 90% of the data, and that 10% moves up like that. But in reality, that's not how this works. We're doing it shuffled, so that you can imagine little bars going up and down these lines, though they don't necessarily correspond. So what we do is we basically, for each one of these purple bars, we go through and we fit a model, and we then see how that model, how well it predicts on that 10%. When we combine all of these together, we're able to basically estimate how predictive the model is, which is absolutely key. We have to remember that what we're trying to do is not to model something and make it look perfect in the baseline. We are trying to model something to predict the future. So this vastly helps with that. Once we put all of that together, then we can basically say, okay, which model does the best? And then we can test that on the final 30% to get like a real estimate of what the predictive power of our model is. Move to the next slide. Now for us, it becomes a little more complicated, because the temperature, season, and weekday, weekend, all variables that we're interested in, they're not uniformly distributed, which means that we can't uniformly or just pick from these as if it was a normal distribution. We have to actually do a stratified k-fold cross-validation, where we stratify within the temperature, seasons, and weekday, weekends. This means that basically, if you were to pull out the test set and the train set, they would look very, very similar to each other, which is what we would like, because of this stratified bin sampling process. ultimately, all of this allows us to do within sample testing so that we don't have to rely on comparing 1 meter to one in year 0 to the same meter in year 1 and just hoping that we are able to get the best answer. Instead, we can just do it within the same year. This would also allow us to, as I mentioned, to assess the model accuracy and predictability. It'll help to alleviate overfitting, because if we're overfitting, we won't see the same positive predictability that we would otherwise. And this will also help steer us in model selection, hyperparameter selection, that sort of thing. We can jump to the next slide. Now, there's a whole bunch of questions that I thought people might have, went ahead and addressed some of them. So everything that I just discussed sounds a whole lot more complicated than what we're doing. Yes, you're right. How do we make sure that instead of taking like the 30 seconds that it takes to fit a model now, that it doesn't jump up to taking 3 minutes or 10 minutes, because that's going to make all of this methodology just a complete waste of time. Well, we can switch, instead of doing this exhaustive grid search, we can switch to a global optimization scheme, and we will find that we will get major computational efficiency increases. So, next question. Why would we want the old model at all? Because you might notice that I didn't actually talk anything about doing like a multiple linear regression or just kind of standard approaches as from a data science perspective. And the reason for that is that we think that the cooling and heating degree days are extremely useful for disaggregation. This allows us to have some estimate of, can you install a AC unit and see some sort of benefit in the south. So we want to preserve that, which means that I'm kind of constrained to needing a model that still preserves having heating and cooling degree days. What we might do, though, is to look at adding some changes to the functional form. I don't think Adam showed it in the plots, but I found cases where the change from a temperature independent to like cooling degree day or heating degree day, it's definitely not a just on-off switch that you get by doing these the combination, the piecewise linear combinations. So instead, what I've done is I've added an option, or started to work on it at least, where you can basically have an exponential that basically creates a smoothed version of that. I'm also not opposed to any other functional forms that people might have ideas about. Lastly, why do we not want to use AI machine learning? Well, this is really about making sure that we keep our models as simple as possible, but as complex as needed. And once we go the route of AI machine learning, we're going to lose that ability to understand what's going on in the model. It's going to predict really well, but you won't really know why. If that were necessary, we would go that route, but so long as it's not necessary, we won't. We have, however, used kind of a quick and dirty neural net to inform our current ideas about development. So for example, the thermal lag that I was talking about was informed by a neural net that Armin, my fellow data scientist here at Recurve, put together, where he included, I believe it was the current temperature as well as the up to a week. So each day, the average temperature to a week behind. And what he was able to see was that what was important was having at least once you got to 3 days, it kind of, you had diminishing returns pretty significantly, but you could go up to -3 days. And so we're kind of using neural nets and these advanced techniques to help guide us. And you go to the next.
Great. Just a really quick note on comparison groups. Comparison groups are still important because they help remove model bias, and model bias can come in a few forms that are important. One form being external factors like global pandemics, economic recessions, inflation pressures, things like that. And we're not going to be adding like a global pandemic variable to CalTRACK anytime soon. I hope folks are on the same page as we are with respect to that kind of thing. But we don't want to rely on comparison groups to alleviate things like seasonal bias. They do alleviate seasonal bias, but we don't want to rely on them as much for those purposes. So it's just to say comparison groups are still important, but they're not going to be part of what we're focused on here. And Phil, we have a little bit of time. I still have a couple slides on the technical steering committee, and I have a slide or two on like how to contribute. And we have a little bit to get through on GitHub. What I would suggest is this is being recorded, so anybody who has to jump can jump. But let's stick with this and finish this out. This is a heavily packed first meeting, but we're trying to get a lot out there. And the GitHub stuff, I don't want to shortchange the GitHub stuff. So if you have to hop, feel free to hop. But let's keep on track here. And Phil, why don't you take the baton?
Sure, I'll keep it very brief because the core of this is to understand how to contribute. Adam, would you grant me screen share, or whoever is controlling that?
Absolutely, Phil. 1 second. You've got it.
All right. Okay, so I'm going to pull up the CalTRACK repository. Actually, this is the OpenEEmeter repository. On GitHub, we have, which is where we store code for the methods and documentation of the methods. There are 3 repositories here. There's the OpenEEmeter repository.
Phil, I don't think we're seeing your screen.
Oh, you're not seeing my screen.
If you're lost up at the top where it says view options, you click that and it says shared screens, Adam or Phil, and switch to Phil.
Ah, yes. Please stop me if I keep talking and you still can't see anything. We have an OpenEEmeter organization here on GitHub with 3 repositories. We have the main OpenEEmeter repository, which is mostly the code.
Sorry, still don't see it. Sorry.
Are other people having that problem too?
Adam, it might be easier if you stopped your screen share. I think it would probably.
Oh,
Phil.
maybe that is the issue. There we are. How's that?
How are folks able to see it now?
Yes, that works.
Great
Thanks.
for me.
Okay,
sorry,
Thanks for
guys.
speaking
It
up
takes more than one physicist to figure these things out.
OpenEEmeter repository, 3 repositories. The main one of interest here is the CalTRACK repository, which has the documentation of the CalTRACK methods. Although we've spent some time talking about the OpenEEmeter, which is the Python-based implementation of that, and EEweather, which are some tools that were broken out of the OpenEEmeter at some point to deal with all the weather data, because that's so important, mainly temperature data. Although, of course, we're talking about future sources, and many people have shared some feedback about how that could be easier to use. So let me just jump into CalTRACK. Really what we're talking about here is, number one, how can I see what's going on? What's underway? And how can I contribute to that? For those of you that participated in this process before, we relied heavily on the issues section of GitHub. We'll be doing that again. I've closed out all the issues that had been open previously, so that we have kind of a blank slate to start with here. When you want to, so let's talk about what an issue is and what a pull request is. If one thing that Adam will mention when we talk about how we're going to be accepting contributions here is that we're really looking for specific changes to the methods. And what that means are, a line of, some words that are different. You can go in here into this section here and look at methods.rst. RST stands for restructured text. These are the CalTRACK methods right here. You can read through them. And so what we're looking for are specific additions here, or edits or changes, something to the language here that will help clarify or change these methods. We'll be versioning these and tagging them so that, if as we make changes that you can always go back and kind of look at a previous version. But ultimately here, there's an option if you log in using a GitHub account. Anybody can sign up to do this. This is a public repository. You can go in and edit this file, make changes. You won't be able to commit those directly, but you can make a pull request. And a pull request is a way of capturing all the changes and having some discussion around it. You're not quite ready to make a specific change. can of course also create an issue. Hey, I'm running into this seasonal bias issue. I have a thought for how to fix it and would like to test it. When you do that, you'll have an option to create a new issue here. You'll be able to get started. There's a CalTRACK template here, which will walk you through what you need to do to kind of describe that issue and what we might do to test it. And as you've seen, we've got a few things to start off with here so that we can hit the ground running. But as we get deeper, folks will have other suggestions. Please use this as an opportunity to submit those, and then that will make it much easier to have further conversations or to incorporate it into further working group meetings. I know that was very fast. There's lots of documentation online about how to use GitHub if the tool or the interface itself doesn't make any sense here. And we can follow up on this later, but I just wanted to give folks a really quick view into the specifics of how to contribute here. So Adam, I'll pass it back to you unless there's anything else you'd like to cover here.
Thanks, Phil. Are there any quick questions for Phil, just right out the gate? Okay, we will, I'm sure, collectively, myself included, get more familiar with the GitHub environment. I see Ken has a hand raised. Ken, do you have a question or thought?
It was back a ways and it's not relevant now.
Oh, okay. Well, we can follow up, Ken, as always.
It was just a detail.
Sounds good. All right, I'm gonna just round us out here, and I just have a few more slides. And again, they're kind of like process and logistics oriented. So first, I just wanted to let folks know who is on this technical steering committee. The steering committee is really like they are tasked with kind of keeping things on the rails and making some decisions, because I think as a group, like we need to all weigh in, and at times like not everybody may agree. And so the technical steering committee also needs to kind of be mindful of the code and manage like the actual code base. And we don't want to be breaking the code base for obvious reasons. So a lot of these folks are people I think that are familiar to most folks here and have been involved, several folks have been involved with CalTRACK in the past. So there's me, you know me at this point, McGee Young, who is heavily involved in CalTRACK 1.0 and 2.0. We're really happy to have him back here, and we'll be definitely using some of his wisdom and expertise in this whole process. Phil, who you just met, if you haven't met him before. Travis, same thing, and Steve Sufian. And then additional resources. I'm sorry, Steve is with Watt Carbon. Yeah, my fat fingers typed a little, or copy and pasted a little too readily there. So Steve is with Watt Carbon. Thank you, Phil. And then additional resources are going to be Armin, who Travis introduced a moment ago. Armin is a data scientist here at Recurve, and he has already started to do some like exploration of weather data that can be used for solar PV modeling, which is going to be super useful as time goes on here. And we'll be involved. He's an expert in like neural nets and has recently done his PhD at UC Riverside. So we're excited to have him on board here. And Jason Chulak, who is also at Recurve and is an engineer. And then anybody else, I left this open, question marks for anybody who really wants to dive in and contribute. I mentioned earlier, just as an example, that there are really good ideas and potential improvements that could be made to EE weather. Maybe there's a subgroup of folks that can really dive in on that, or groups that can help with particular aspects of testing, and obviously Phil just talked about how folks can contribute with ideas. Ken, go right ahead. Or maybe that's the same hand.
Might be the old hand.
Yeah, it might be the same hand, but it was raised earlier. All good, all good. Okay, so just to round, was there a comment?
No.
Okay, sorry. Sorry, Ken, my bad. So just to round us out here, I think we've kind of hit on a lot of these points before, but it is worth saying that all of this is under the umbrella of the Linux Foundation, and we're really excited to have their partnership. There are a number of open source projects in the Linux Foundation, and they do have a set of guidelines and principles that people should follow. And so the mission of this project really is to develop, open source framework. The Linux Foundation is all about open source code. So everything that we're going to be developing for these models will end up in the OpenEEmeter open source repository, or EEweather, or ancillary libraries. This needs to be like a production ready piece of code. And it needs to be transparent, well commented. This needs to be a good documented piece of code. And we want, through this process, hopefully, to develop others who can contribute and have ideas that actually have time and space to work on these things. At the same time, obviously, everybody is resource constrained, everybody is bandwidth constrained, and it's not fair for us to say, you have to do this, you have to do this, you have to do this. We're not in the business of like assigning others to aspects of this project. It's really not our place. But if you are really interested in something, please do reach out, file issues, those kinds of things. We'll find ways to work together. There's a whole bunch of links here to like existing methods, existing libraries, code. I won't get into all of them. And just some principles, just stressing what Phil kind of already mentioned, that solutions and testing are really a foundational process of methods development, and we're fully expecting that we're going to be doing a lot of that. Recurve is willing and ready to devote real resources to this, but we don't have infinite bandwidth by any stretch. And we understand that people rely on these methods, so we want to be cognizant of that. And so we want to make sure to produce something that is genuinely a step forward. It's not going to be perfect. I will guarantee you there will always be new things that we could look at, other aspects that we could dive down. And we will not, I promise, we're not gonna be able to get to everything or every idea that people have. We're going to do our best though. So with that being said, I just want to kind of round out and let folks know that there will be a different leadership very likely at the next meeting, because I am going on paternity leave in like a week or two. So I will be out for like a month or so, and we'll look to get the next meeting scheduled, but you will be in very good hands with the rest of the folks that I've already mentioned and have already contributed here today. So with that, if there are any final comments, we can stick around or we can let folks go. And thank you so much, and sorry for being about 5 minutes over here. I really appreciate people sticking around. Any last comments or thoughts? All right, well, with that being said, have a great Thanksgiving, everyone. Thank you so much for coming today. We will be in communication about the next meeting, and I'm hopeful that we'll, be able to move quickly and show some progress to everybody as time goes on here. So thank you again, and we will talk to everybody soon.